Okay, 6:15, let's start. So again, welcome. Uh, in the way that I typically do my modules, right? As some of the students in the class who were with me for modules in the past semester, typically I always start with revision review. Okay, so let's do that, right? Let's do that. So remember last week, we were talking about adaptive control. And then we said, okay, let's start off by looking at the almost the simplest possible example so that we have a clear idea on what adaptive control is actually all about. So what we then said was, okay, let's, for example, even look at the simplest system, right? Basically, a linear dynamical system, first order unit. And what would we do if we were trying to control it, right? Typically, if we were trying to control it, we would say, okay, as a result of having finished controlling it, right? We would want to be sure that somehow, if I put in some kind of a command, all right, if I put in some kind of command, I expect that after I finish controlling it, it should respond with some rise time and then basically make sure that it matches what I want to command it. So with that kind of description for what we expect, basically you've actually set what you specify on what you expect in the system as a reference, right? Okay, so if you are given this system and you want to do this kind of a thing, all right, so even before doing adaptive control, you have to say, okay, how might I even do this kind of a thing? So clearly for this simple system, you would say, okay, I have the output measurement, I take it, multiply by a gain, right? Then I have my command reference signal. I multiply it by a scaling gain, put it in. This would be quite typical. And as we saw, okay, indeed, you do that, right? This is what you specify, right? So this would be the kind of control that you would put. So let's see what would happen. You put the control inside and then you check, indeed, after putting the control inside and simplifying the expression, indeed, what would then happen is that there does exist a control gain for theta, and there does exist a control scaling gain, right, for k, all right, such that, all right, if you choose this theta down here to be the perfect gain, so we denote that by theta star, and then you say let it be what you want it insofar as the reference model is concerned, right? So, and that can be calculated. This is from the system, all right, the plant that you try to control AP. KP is also from the plant. So if you knew all of these things, certainly theta star can be calculated. Similarly, right, KP is from the plant. If you say you put this as a scaling gain and you want it to be equals to Km, right, from your reference model specification, certainly, right, certainly a perfect number K star exists, all right, such that it will exactly meet this expression, right? So these numbers exist. So if you put in these numbers, it'll be exactly like that, all right? And then if these were the perfect numbers that you put in, you can check what the tracking error might look like. The output tracking error is E1 YP minus YM, right? A simple calculation. All right, with that, then you can see that just simplifies to E1 dot equals AM E1. And certainly this will work. This will work in the kind of arrangement that you have. If you put in these perfect gains, then once you put in these perfect gains, then indeed, all right, the tracking error will be 0, and you're exactly getting the kind of closed loop you specify, right? So this is essentially the whole starting point. Okay, then we said, okay, we still want to do this, but now is a situation where we do not know, all right, the numbers, all right, of the parameters in the system that we want to control, the plant, right, that we want to control. We don't know these numbers. So obviously, if you don't know these numbers, you cannot exactly calculate K star and theta star, right? You cannot calculate K star, theta star, but you still want to do the same thing. All right, so we still want to do the same thing. So then basically what you can see is that starting from this arrangement, right, clearly you know this structure works. This structure works, except that you don't know what number perfectly to put in down here, what number perfectly to put here. But we know this structure works. So what we can do is we say, okay, why don't I put in a control gain, but let it be varying in time. I put in another control gain, but let it be varying in time. All right, and let me find a way to update or to adapt. That's where adaptive control in this way can come in. Find a way to adapt how these time varying gains will change with time, so that I still can get, can get the fact that I will get the closed loop that I want, closed loop performance that I want, even though I do not know the numbers of the plant, of the system I want to control. All right, so this is where, all right, we can begin to start to look at the whole idea, the whole concept of adaptive control. So indeed, we take the same structure, still take theta minus yp and k minus k times r, except that because we don't know what perfect numbers to put in, we let it be time varying, and we will have to decide how to make this time varying. Okay, so here, as I said, we then went on, we said, okay, this is how to make it time varying. You will take your theta of t and you will update it like that. All right, you will take the output tracking error exactly in the diagram above, which is yp minus ym. Yp you can measure. All right, then take some number, some positive number, any positive number, gamma 1. Then I say in this particular approach of doing adaptive control, all right, the most direct way is to just, even though you don't know the number kp, some simple experiments can show you the sign of kp. So you can put minus sign of kp, gamma 1 yp times E1, and that would be the way you would update theta. And the way you would update k would be similarly minus sign of kp, gamma 2, again any positive number. Then take the reference command signal. Reference command signal you know because you are the user, you generate it. So this one also you know. And then E1 you can measure is yp minus ym, and you take it like that. So this would be the control law. This is the adaptive law. Okay, then we say, okay, how does this work? How does this work? Okay, so this is where essentially this is the whole idea of how we might do adaptive control. And as you can see now, it no longer becomes like your signals and systems in your undergraduate or even in your standard linear systems, even though linear systems is required as a background, right? But it really, it's still a control problem. But now you look at this thing and control gains are like that, all right? Time varying, and to be specified on how to make it time varying, and you specify how to make it time varying. But when you look at a system like this, all right, you can no longer talk about eigenvalue equation of your system matrix or the S-plane or root locus. You can no longer look at that. I mean, it's still signals and systems, right? It's still dynamical systems, but we have to now look at it from a different way. Okay, so the way we saw from last week, right, was to say, okay, let's look at the system now. In this way, we are doing adaptive control, and let's see what might be the signals that we are interested in. Right, clearly we'll be interested in the tracking error. We know that a perfect number theta star exists, even though we may not know what it is. We are putting in this control gain into our system. All right, so this exists. We don't know what it is, never mind. This is what we're using. And clearly, theta minus theta star is the parameter error in this theta. Because if we are able to exactly make this theta star, the parameter error here will be 0. So certainly we are interested in this parameter error. So similarly, therefore, we are also interested in the parameter error in this other scaling gain control, which we are also making time varying, and we know there's a perfect gain. So we call this error C of t. Right? So these are the error signals we're interested in. So as I said, when you look at this now and begin to see how the system is developing, evolving, it may be quite typical to say, look, I'll be interested in some kind of energy-like function. All right, energy-like function combining all the three errors, which will be E1 squared, P squared, C squared. All right, which, if you didn't have these scaling numbers, would just turn out to be a sphere in three-dimensional space. But basically, if you just simply choose a sphere, it wouldn't work because in the way that we are doing it, various numbers come in. So you have to somehow shape your energy surface. And the proper way to shape that energy surface is now, instead of taking a sphere in tree space, you take that gamma 1, which you're using in adaptation, all right, put that in the denominator, put magnitude of Kp, all right, and then put magnitude of Kp here over gamma 2. So remember, this now becomes an ellipsoid in three-dimensional space. So ellipsoid in tree space. Okay, remember, we are just using this conceptually as an idea to see how the system behaves. Certainly, basically, this ellipsoid exists, okay, even though we do not know the value of Kp, all right? In fact, we don't know the value of E squared because that's the parameter error theta from theta star. We don't know theta star, so we don't know P. So never mind, even though, many things in there we cannot exactly measure, but as an idea, as a concept, this exists and is valid. All right. So this is an ellipsoid in tree space. Then we say, okay. In order to understand how our system is adapting, clearly we would want to see how this ellipsoid itself is behaving with respect to time. Okay. To see how this ellipsoid is behaving with respect to time, you're saying you're interested in the time derivative of this ellipsoid. So we say we look at the time derivative of this ellipsoid. It's not difficult. All right. So I put a half there. So you differentiate this. This just becomes 2E1 dot. All right. This becomes 2 phi dot. This becomes 2C dot. So that's exactly what we write down. So this is the time derivative of the ellipsoid. Then we say you look carefully at the various terms in this time derivative. For a start, let's look at E1 dot. E1 was Yp minus Ym. So E1 dot is clearly Yp dot minus Ym dot. But Yp dot was originally from the system, right? Yp dot was AP plus Kp times U. So we put in the U exactly as it is, which is Kp theta Yp plus Kp K times R, except we separate out theta to be P plus theta star. We separate K to be C plus K star. Right, Ym dot is, as we said, specify Ym plus Km times R. And you already know that, these K star numbers in here, when you multiply and add them together, when you multiply, give you exactly Am and Ym. So now, if you now further simplify it, this now simplifies to E1 dot equals to Am E1 plus Kp, P times Yp plus C times R. So this is the first dynamical equation in the errors which we are interested in because it comes up here. Then we are also, of course, interested in P dot and C dot. All right, and that one is more straightforward. And in fact, that's exactly why we designed the adaptive law in that way. All right, because as you see, we're interested in P dot, but phi is theta minus theta star. Theta star is just a constant perfect number. So basically, phi dot is just theta dot. But theta dot was how you design your adaptive update law for theta. So that's why you see this is where the design freedom comes in. We were the one to specify this design of the adaptive controller. So similarly, this is just equals to how we design the adaptive law for K dot equals to minus sigma Kp gamma 2 E1 times R. So we get all this, we substitute all these things back. So we substitute all these things back, all right? If you check that carefully, all right, if you now check that carefully, you substitute all these things back. Okay, this is E1 dot, this is P dot, this is C dot. Okay, now you begin to see why we did it that way. All right, because now this is the number Kp, the magnitude. This is the sign. When you take the sign of a number, multiply the number, you exactly get the number itself. All right, gamma 1 cancels out. Then when you look at the remaining terms down here, it's exactly equal to this first term. So you see, the way we design theta dot, this is basically theta dot, was such that we cancel out this term. All right, this way of doing it comes up quite often, all right, in control systems, not so much in linear systems, mostly in non-linear systems control, it comes up this way. But as I said, it does come up in linear system if you look carefully, all right, in your 5101, if you had done all the way to observer, reduced order observer is there. This kind of idea is also there. All right, in my own undergraduate module, some of you here are for my own undergraduate module. Some of you, Tang Jiwei, Li Haipeng, Wang Xiaoxia, Yi Ming, Bao Lichen, Wang Yibo, Zhong Jialun, the few of you here. I don't know whether one of you is sitting in Chua Weixian. All of you from my class last year, we didn't have time to do it, but if you look in the notes, it's also there. Reduced order observer, this was the basis of the design. All right, and you basically choose your design equations so that you are able now to handle the things that come up. So this is K dot. This K dot is how we design it, and you can also see same kind of a thing when you multiply it out. This exactly equals to this second term, cancels it out, leaving us with only the first term. All right, leaving out with this only the first term. So so that was why we designed it that way. So you will now see that leading to V dot. All right, remember V is the ellipsoid in tree space. So this is its time derivative. This is now AM E1 squared. In the way that you would have designed your reference model, AM would be values for the stability of the system sufficiently far. So AM is a negative number. So V dot now is less than or equals to 0. Okay, so now this is an important middle stage result. All right, we're not yet there. This is just something in the middle. So you already have the ellipsoid in tree space, which is V. You found its time derivative and is guaranteed to be non-positive. The time derivative is guaranteed to be non-positive. Okay, so then what that means is that, okay, if you now have this ellipsoid and you've guaranteed that its time derivative is always less than or equals to 0. So remember I told you last week, I said, look, last week at 6:15, we started the class, we started this simple adaptive controller. At that time, when you started that simple adaptive controller, all right, I mean, it's a system. At that time, the system, there's some value for Y. I mean, you know, and okay, it may be big, it may be small by some value. You started off the reference model. Okay, your reference model will be well behaved because that's what you expect of the closed loop. So when we started off last week at 6:15, Yp minus Ym last week at the time T0 at 6:15, Yp minus Ym has some number. So it will be E1 squared at T0. Okay, you started off with some value for your control gain theta of T. All right, if you don't know what to put, typically you might put 0. Or if you know what to put, you might think that it's somewhere near 1.5, you put 1.5. It doesn't matter. Okay, whatever theta is minus theta star, which is also a number, that will be 3. So at 6:15 p.m. last week, this is also a number, the error. It's a number. All right, similarly, K minus K star at 6:15 when we started is a number. So at time T0, this was a number, and you can calculate the exact value of the ellipsoid. If you know all the quantities, you can calculate, and that will be some number at 6:15 last week when we first started. Then the result that we have guaranteed ourselves is that whatever number you start off with, this number can never grow. This number can never grow. So if this number can never grow, then the obvious conclusion is that if this number can never grow, the first conclusion is that, okay, after this, what must happen is that the tracking error, all right, it may grow larger because remember, this is not a sphere. This is an ellipsoid. So for a while, the tracking error may even increase, but you know, whatever it is in that ellipsoid, it cannot escape the ellipsoid. So it may grow, but whatever it is, it cannot run away to infinity. So it's bounded. So the tracking error is bounded. Similarly, the parameter error, theta minus theta star is bounded, c minus c star is bounded, and this will be bounded for all time from your beginning time. So I put 0, but it could be 6:15 last week, then it's t0. So it's bounded for all time, bounded for all time. And I've just shown you that, okay, in this system, the way we constructed it, all right, all signals exist on the timeline. So even though, as I said, you know, even for simple nonlinear systems is very unpredictable. All right, I can construct for you a very simple nonlinear system. I told you last week that anytime you want, you tell me you want this system to disappear in 1 second. I can write the equation for you such that in this nonlinear system, okay, the signals completely disappear. And after one second, you cannot even find the system anymore because the signal has disappeared to infinity before 1 second. You say 1 second is, you know, very long. You want it half a second, I can also make it so for you. But here, okay, I've just finished showing you that in our adaptive controller, which is also a nonlinear system, this can never happen because the signals exist for all time. Okay, so that's the first step. Then we say we do it further. We take the v dot signal, and now we take its definite integral from 6:15 last week to any time. All right, anytime. All right, we started 6:15, so we can let it continue the whole week up to now, up to now, up to now. So we integrate up to now. And even if you integrate up to now from last week 6:15, it will obey this relationship. All right, and as we said, we simplify that because you know this, whatever it is, VT, this is a positive number. So if we now remove this, we take a more conservative overbound is less than or equals to T0, which would be a number. This is the number at 6:15 when we started last week. It's any number, it may be large, whatever. You know, even if it's a large, it's still a number. It's still a number, okay? Okay, it's large. Okay, it doesn't matter, okay? It's still a number. Okay, so whatever it is, you know, if you now begin to rewrite it, all right, noting the E1 squared, you now begin to see that, okay, basically in the way we have done our adaptation, starting from 6:15 last week, integrate this E1 squared all the way up to now, it must always obey this relationship up to now. All right, even if we continue up to the end of today's class, continue till after Chinese New Year is over, it must still obey this relationship. And it's true for all time. Okay, so what kind of signals will obey this? This is basically a signal belonging to the class of capital L2, right? For those of you really who have studied properly real signals and systems, right? So, okay, what kind of signals obey this? Okay, so as we said last week, we said, okay, signals that may obey this may look like that, okay? The orange one, okay, let's see, okay, it goes, you know, and then it goes. So the orange one cannot, because, you know, the orange one continues to accumulate integral, and at some point it's going to violate this. So it cannot be that kind of orange signal because the orange signal will violate this. So maybe it's the blue kind of signal. In the beginning, you adapt, you know, it's not behaving too well, and then maybe it was okay, then it's not too well, and then after a while it must settle down. It must settle down because, you know, if it doesn't settle down, it will violate this condition. So the only kinds of signal that would obey this capital L2 condition would be that it must be a signal that settles down, all right, and be square integrable like this. Okay, so it's likely to be the blue kind of signal. Then I said you have to be very careful because in signals and system, okay, it can be the blue kind of signal, but supposing with the blue kind of signal, I say your blue kind of signal has superimposed on it suddenly a spike like this, a spike like this, a spike like, and it happens. It happens, all right? For systems that are not well controlled, you will see these kind of things happening. Okay, and if you look at integration theory properly developed is based on what is called measure theory. All right, so the measure is basically the underpinning timeline, the support set. All right, so you are now basically integrating over the tau, okay? But for a spike of a signal, at the point of the spike, basically it is infinitesimal. It carries zero measure. D tau is zero. So basically, a blue kind of signal superimposed with the red kind of spike will still satisfy this condition because the spikes accumulate no integral. The spikes accumulate no integral. So there's a danger that is this happen, and we don't want that because we don't want an adaptive control where mostly it's behaving fine and suddenly it jerks. All right, we don't want that. Okay, so let's check further. We said for ourselves now, we can look further because this alone is not good enough. This alone is not good enough. We checked further and we saw that, okay, we also have this expression E1 dot equals to AM E1 plus KP P times YP plus KPC times R. E1 was guaranteed to be bounded. AM is just a number. KP is just a number. Phi was guaranteed to be bounded. YP is, okay, E1 is YP minus YM. E1 is bounded. Ym is bounded. Therefore, YP must be bounded as a consequence. So Phi is bounded, YP is bounded. KB is just a number, C is just a number. R is your user-defined reference command signal. So for a useful system, this is also a bounded signal. So separately now, as an additional step, we look at this and we say, look, in our system, we also have the result that the E dot signal is itself always a bounded signal because we can see this from all the components. All right, so E1 dot is bounded. All right, this is bounded. Okay, so since this is bounded, then we have this particular property 54 together with the L2 property 53. Then only then with these two properties can we finally say that indeed we have achieved what we intended in the adaptive control, that if we set up the adaptive control in this way, we are guaranteed that indeed we will achieve our tracking error. Okay, so this is what we did last week. Okay, with that, let me go now basically to the typewritten lecture notes, because my students know that typically what I would do is basically I use my own typewritten lecture notes, but I would always prefer to develop the same material at the same time by hand, as you saw last week. Right, so here basically this is what we have done, all right, which is in parallel with the typewritten notes. We say, okay, the first order system. Basically here I've written in operator notation, but it's the same thing, right? So if you do all of that, you now, and then you begin to put in this adaptive law, all right? Look at the ellipsoid, carefully look at this, all right? And then step by step, you can ensure that this is what we have done, all right? And then we've just guaranteed indeed that our adaptive controller works. So this next slide here essentially summarizes this first order, the adaptive control for this first order system. Right, so I put everything here in place. Okay, here I've simply said that if you don't know what the gains are, you may want to put 0. But you can also see that in all our analysis, we don't need you to put it to 0. You can put it in any number. All right, if you know something and you prefer to put another number, that's fine. That's fine. Okay, it's arbitrary starting gains. All right, arbitrary starting gains, and the system, you know, starts, and then you put these things and you put this whole thing together. All right, and it works. All right, so this summarizes the entire situation. Okay, and in a way, this is, if you like, this is quite nice. This is quite nice because with this, basically, if you just want to do some simple experimentation to begin with, go ahead, go ahead. I mean, you know, all of you have MATLAB, all right? All of you have MATLAB. You can actually start to program MATLAB and begin to explore this. All right, you can begin to explore this directly in MATLAB, put together a simple system, any simple system, then set up your reference system, set up your adaptive controller, and you will be able to see exactly that indeed, no matter what starting gains you put, all right, and even with your system, no matter how you start the system, okay, just this system, start it with any initial condition, all right, set up your reference model properly, of course, stable reference model, okay, depending on what you want. All right, with a proper reference signal. And your reference signal can be anything. It can be a set of square wave, it can be sinusoidal, multiple sinusoidal, doesn't matter. All right, as long as it's well-behaved reference signal, this whole thing will work, guaranteed. All right, so in some ways it may be good to start because I've already uploaded for you your CA1, CA3 assignments. Basically, they will be more complicated than this one, but this is a good starting point. Once you start, at least you will have some practice. Okay, so this is now what we have just finished. All right, this is what we have just finished up to last week. Okay, let me now even push on further. Okay, wow, this is just a block diagram picture. Let's ignore it. Okay, in the way that we have done it, even though I didn't say it, all right, basically the approach is almost a parallel approach of the ideas from the so-called direct method of the Lyapunov. All right, so in our module, we don't have time to go in deep into the Lyapunov stability theory, but basically what this approach says is that, first of all, whatever system that you put together, in this case, our adaptive system, first of all, it says write it properly as a complete state variable system. All right, complete state variable system. Okay, again, as I said, that's why I said you basically, okay, even though you may have signals and systems, you may have undergraduate control on transfer function and root locus, but really I hope you are familiar with state variables. All right, because as I told my students from my last semester class, it was an undergraduate class too, except we are doing state variables. I said, look, state variables doesn't mean you have to be linear. All right, a set of state variables. What was a set of state variables? I told my student, okay, they will remember. I said this so many times to them, right? I said a set of state variables is simply this. You tell me all the signals, which are your state variables, all right? Let's say you have 3 state variables, x1, x2, x3. Then, okay, if you tell me these 3 are your state variables, this number, these signals, x1, x3, x1, x2, x3 must appear on the right-hand side. No derivatives, just x1, x2, x3 in whatever kind of way. It can be even non-linear. All right, so it doesn't have to be linear, okay? x1, x2, x3 must appear on this right-hand side. No derivatives with whatever kind of non-linear functions, with whatever kind of time-varying additions, doesn't matter. But x1, x2, x3 must appear on the right-hand side with no derivatives. Okay, so my student will remember that. Okay, Yiming, Haipeng, Xiaoxia, Jialun, Li Chen, Yibo, then Ziwei, okay, you will remember I said this so many times. I said your state variables must appear on the right-hand side, no derivatives. Then the same signals must appear on the left-hand side and first derivative only. This is what state variables is all about. So the Lyapunov direct method say, okay, you build this system. After you build this system, you take everything and put it together and write the proper state variable. Then find a way to write some scalar function, and we call it the energy function, the ellipsoid function. All right, but basically this scalar function, whatever you do, must have these kind of properties. All right, when you look at it, when you look at your state, because you're writing your this so-called scalar function v, and it is built on your state variables. All right, it's built on your state variables. The function v must first of all be a positive definite function. Positive definite means very specifically positive definiteness. It is not just a positive function. Positive definite function says you make this function for me as a function of your state variables. Then if you say it's positive definite, you must be able to write for me and find for me a continuous non-decreasing scalar function of the norm of your state variables, such that your V scalar function overbounds it from above. Okay, later I'll show you exactly what this means. All right, because a lot of people, even in research, make the mistake. They say, oh, positive definite function, they just find a positive function. No. Okay, it must obey this kind of overbounding. Then there's a second part. It says, okay, if you want more properties for your system, at the same time, you look at a property called decrescence. Decrescence is quite similar to positive definiteness, but it now says you find a similar function like the alpha, but you call it beta, and this function overbounds. Remember, alpha underbounds V for positive definiteness. Beta must overbound V for decrescence, and beta is also a function of the norm of your so-called state variable. So you must be very clear what your state variables are. Then after that, it says, okay, you take this scalar function, you show me that its time derivative is negative semi-definite, all right, like this. And in addition, you can also show me one more property, that if this scalar function that you construct, all right, while being positive, in addition, if it is what is called radially unbounded, radial unboundedness means that you take this alpha function, which you have shown to exist, to underbound your V, and you show that this alpha function that you're able to write has this additional property that as norm of x tends to infinity for this alpha function, the alpha function itself also tends to infinity. Then you also have this last property of radial unboundedness for your scalar function V. All right, so if you now have all these functions, several combinations of it, but we're not interested in all these lesser combinations of A and B. We are only interested in the most powerful condition of C. All right, that you have all of these properties. Then it says that your design, because we're using this to design an adaptive controller, it says that your design is uniformly stable. So you've seen, because I didn't even talk about the Lyapunov theory, I've shown you all signals are bounded and exist for all time. All right, and then I've shown you even more. But now, you know, if you now go back to how the Lyapunov theory describes it, this is the equivalent. It says, look, you know, if you have all these properties, all right, your system is indeed uniformly stable in the large. In the large means in the entire state space. All right, and you saw we have that, All right, because if you now go back and look, we have that. Because it was in the entire state space. All right, because you remember what we said was that when we started at 6:15 last week, you can start anywhere you want. Your YP, you know, when you started off your first order linear system, you know, you can have any initial condition, you can start anywhere. You can put your theta gain anywhere, your K gain anywhere, it doesn't matter. You can start anywhere you want at 6:15 last week. You can put it anywhere and we still get all these results. So that is the equivalent result of saying that this is a globally stable adaptive controller design, or equivalently uniform stability in all of your state space defined. Okay, I'll go to that very, very specifically shortly in a moment. Okay, so now as you can see, going beyond what we had done, all right, last week, I'm now showing you how it links to the rigorous methodology of the Lyapunov theory. Okay, let me push on. We will use some other ideas in stability theory. Okay, this one will come from your 5101, also from my 4302 last semester. If you now have a standard linear state variable system, okay, with some initial condition in n dimension space, all right. If let's say you say this system is stable system, then what you've just told me is that eigenvalues of your system matrix are all negative, right? Because that is what a stable system is, eigenvalues of the F matrix. And more than that, all right, more than that, if this indeed is a stable system, then this particular equation always exists. So remember, now we are looking at a state variable system, linear state variable system, either from your state variables in 5101 or whatever state variables module you have taken before. All right, so this is a linear state variable system. All right, if you now give me a stable linear state variable system, all right, with n state variables. So A is the system matrix for this state variable system with n state variables. Then for this A matrix of this stable system, okay, if indeed is a stable system, you will always be able to write down this equation. You will always be able to write down this equation. All right, that you put your A, all right, take A transpose, all right, then put it with a P, all right, which is a symmetric matrix, plus that same symmetric matrix times A equals to minus Q. Remember, A is from your system and it is stable. Okay, you just told me it's stable. A is from your system is stable. Q will be a symmetric matrix. If you now put any value for Q, as long as it's symmetric and a positive definite matrix, okay, later I'll just quickly review for you and remind you on positive definite matrices, but basically a positive definite matrix. All right, positive definite matrix symmetric. So A you've just given to me as a stable system. Q is something you write down, but whatever you write down for this Q, you must make it symmetric positive definite. So A you've given to me a stable matrix. Q you must write down, and Q must be symmetric positive definite, and it's minus Q. Then you put down this equation, and it turns out that for this equation, you will always be able to find a solution for P. All right, and the solution for P is guaranteed in this equation itself to be symmetric and positive definite. All right, so you will see that P always exists as a solution, and P itself will be itself symmetric positive definite. If A is a stability matrix and Q you will put down, and you put it down as symmetric positive definite matrix. With that, then we will be ready to push on to the next stage, which will be to do adaptive control of a linear state variable system with all state variables measurable. But before that, let me back up a bit and say, look, so what I've just finished telling you is that, look, we've set up, okay, so we did revision, we did review, and we said we've set up this first order adaptive controller carefully and have obtained for ourselves all these results. Then I've just finished telling you that, well, these results are equivalent to this rigorous method of Lyapunov. Okay, now as a very first thing, I will now indeed show you that this is in what we have just done last week is indeed equal to the method of Lyapunov. Okay, and that after that we'll take a break, and then we take a break after I've shown you that. Then we will go on after the break to properly now develop adaptive control for a system with all state variables measurable. Okay, so first of all, let's show that indeed whatever we claim about the Lyapunov direct method was already there. All right, was already there in everything that we did before. Okay, so let's make sure. Okay, so let's go back now. Okay, let's now work on these things, and then let's begin to carefully look at these things. Okay, so as I said, let's begin to carefully look at these things. All right, so remember what the Lyapunov method said. The Lyapunov method said, okay, you write down your system in state variable form. So as I reminded you, I said, look, state variable form is exactly this. You tell me whatever your state variables, all right? All right, if you tell me you have 3 state variables, then you better be able to write down your x1, x2, x3 signal on the right-hand side. No derivatives. It can be with all kind of nonlinear function, all kind of time variance, doesn't matter. But you must be able to write down x1, x2, x3 in this one on the right-hand side with no derivatives. Then x1, x2, x3 must appear on the left-hand side and first derivative only. So that would be state variable system. All right, state variable system. Okay, you can start with any initial condition. Okay, then Lyapunov method said, remember, it said you must find that scalar function obeying the properties of positive definiteness, decrescence. You must check that its time derivative is less than or equals to 0. Check also that the scalar function that you have is radially unbounded. Okay, so let's make sure that whatever we have done actually certainly is equivalent as we claim to what has been the rigorous Lyapunov method. Okay, let's go back and look at the key equations that has come up that was already there in our work last week. Okay, so remember E1 dot, remember? All right, we had checked it carefully, was, whoops, no, I don't want that. Okay, E1 dot was, remember, AM E1, right? We saw that was excuse me, AM E1. All right, then plus KP. You can go and double check that. All right, then there was that part P of T times YP of T plus C of T times R of T. All right, so that was the first part. Okay, then remember we also have from the adaptive update design equations, this was equals to minus signum of Kp, all right, and gamma 1 E1 of T times Yp of T, all right, and then that was minus signum of Kp gamma 2 E1 of T times R of T. All right, so we have that. Okay, now stare at this very carefully. Okay, so I have the signal E1. Okay, I have the signal P, C, right? All E1, all turning up on the right-hand side. And I also have this same signal, E1, PC, all right? On the right-hand side, no derivative. Then turning again on the right-hand side, E1, PC on the left-hand side with first derivative only, which is exactly the state variable in the state variable structure as needed to use the Lyapunov theory. Okay, and I as I told you, I could start from anywhere at 6:15 last week, you know, with any initial condition. So it meets my requirement of writing this as a state variable. So I have that already. Okay, then the next thing, remember what we did? All right, remember what we did? The next thing, we wrote down our ellipsoid function. Okay, let me write down this ellipsoid function more compactly. Basically, this is equals to 1/2 of E1 squared. All right, 0 times 0 time. All right, then well, let me maybe even just ignore that. Okay, it's 1/2 of E1 squared. All right, and then magnitude of Kp over gamma 1 of P squared, and then magnitude of Kp over gamma 2 of C squared, right? And then basically off diagonal terms are all 0. So that was the so-called ellipsoid function that I used. And I basically obeyed the Lyapunov method, because the Lyapunov method said, okay, you know, if you want to construct your scalar function, it must be a scalar function of your state variables. So indeed, I use my state variables here. Okay, then it says the scalar function. Can you check for me that you can find an alpha function that underbounds it? Okay, so clearly, you know, if you want me to find a alpha function that underbounds it, is not difficult at all, because, you know, with this structure, all right, in above, All right, in above, what I simply do is I look at this thing down here and just see which one is the minimum. All these are will be numbers. 1 magnitude kb over gamma 1, magnitude kb over gamma 2. All these are numbers. I just look at these numbers and see which one is the minimum. All right, and whichever is the minimum, I'll just pick that because, I can then simply write my gamma because the Lyapunov theory requires me to tell you what the gamma is. I just take that to be the minimum, all right, of whatever the three numbers are, magnitude of 1, magnitude of Kp over gamma 1, all right, magnitude of Kp over gamma 2. I just take whatever out of these three numbers are the smallest, and then basically take the norm, all right, of my state variables, which is above, all right, and then take 1/2, okay, because I had that 1/2 in my v of t, and you can clearly see that here, all right, if I now take the minimum number, clearly, okay, compared to my v scalar function, this was certainly underbound my v. So I've satisfied the Lyapunov requirement for positive definiteness. And here you can begin to see, all right, specifically now what positive definiteness is. Positive definiteness is just not finding any function which is positive. All right, because you can find many functions which are positive. This is no. After you find your function, you better tell me what you must show me a proper alpha such that your v overbounds it, and I've shown you this alpha. Okay, now you can see that decrescence, because the decrescence will be the same kind of idea. Okay, the decrescence, instead of the min, I'll just take the max, right? I'll just take the max. Okay, of all those three numbers in there, and then same norm of x squared times half, and you can clearly see that with what we have done, the beta function also exists, which overbounds v of t, which satisfies for me my property of decrescence. Right, then you saw from what we have done in the control law and adaptive law that what we managed to get was v dot equals to am E1 squared, all right, and that was guaranteed to be less than or equals to 0 because with the choice of the reference model, am is indeed a negative number. So we satisfied the third condition of the Lyapunov. Right, then you can clearly see, okay, the final thing is that, look, since the alpha that I have to tell you, all right, the alpha function which underbounds it for positive definiteness was this particular function, which was min, all right, of all those numbers, all right, times norm of x squared times half. All right, clearly, all right, this kind of function which I've specified for you as my alpha, indeed, all right, for this function, all right, if you check this kind of function as norm of x tends to infinity, then clearly I also have the radial unboundedness because my alpha function that exists, which I've just shown you for this, indeed also tends to infinity. All right, so even though last week, all right, we never said anything about the Lyapunov theory, all right, you can begin to see that everything that we have done conforms, all right, conforms properly to the Lyapunov theory. And later on, all right, as I said, we'll go on to look at adaptive control of state variable systems. First of all, when all the state variables are measurable, all right, and you will see, okay, that essentially, indeed, we are developing along the lines of the Lyapunov theory, and all those things meet all those requirements. Okay, with this, let me pause. Okay, 7:15. So let's start. So as I said in this next part, right? As I said, we have already seen the rigorous underpinnings of the Lyapunov direct theory. right? And next we will go on to look at adaptive control with state variables measurable, right? So this is the next thing we'll do. Of course, in later lectures, as quite typical, we will then say, okay, if state variables are not measurable, only input output measurable, and we still want to do adaptive control, how do we do it? Okay, so that is all here in the plan. Okay, but before I go on and push all ahead, okay, let's remind ourselves of a few things. Okay, let's remind ourselves of a few things. Okay, now, first of all, remember, okay, today, Zoom class, all right, Zoom class. Next week will be in person in our classroom, E30609. So remember, next week will be in person in our classroom. All classes start at 6:15. Okay, so remember that, Then, of course, as I also had mentioned last week, I said, okay, to additionally support you all right, my GAs, all right, Mr. Wang Jiahui, Ms. Guo Haoren, they are assigned to this GA consultation sessions. All right, so the first session is tomorrow in the lab. All right, they'll be there. So 3 p.m. to 5 p.m. So tomorrow is the first Saturday, then also all these Saturdays. I've also work with my lab manager. So my lab manager has updated me. All of you in our module here, all right, you are already programmed for access to come into the lab. All you need to do is, all right, go to E4A0304. Basically, the front door down there will be control simulation lab, but you also see mechatronics and automation lab down there. What you do is you just take your student card, put it against that electronic door lock sensor. Once you put it down there, because you are programmed during this time, the door will open. You go right in to the end. That's where Jiahui and Haoren are. So these are the sessions to additionally help you all. All right. Okay. Then so this is what I've said. Right, then you've also seen I would upload. Okay, so even today, whatever I have written by hand, once I've tidied it up later tonight, I should be able to upload it, and also the Zoom recording. Okay, then I've also now begun to show you those files. Okay, don't panic yet. Okay, we're not ready. As I said, you know, typically we need to wait for the whole set of lectures to be done, then these things will become clearer. But again, just to okay, let's see. Okay, right. So as I mentioned, once we have done all these things, during recess week, we'll set aside proper briefing sessions for the CAs. All right, proper briefing sessions. This will be over Zoom, and it will also be recorded. So those of you who want to review and rethink, so these briefing sessions are also recorded. Then, as I also told you, I said we in our module we don't believe in hurrying. All right, we want you to do your work. After you do your work, think over it, see how to improve it, work on it further. That's why in our module, including my CA, CA1, CA3, and also CA2 later by Prof. All right, the deadline for the submission is all the way in reading week, which is the week before exams. Our reading week is a long time away. April, okay, April before exams. All right, and those will also be set up, and we will let you know nearer that time. All right, so that is basically the plan for how we intend to carefully do these things in our module. Okay, so with that, as I said, the next thing we will do is adaptive control in the case of a state variable system where state variables are measurable. But before that, quite typically, let me pause again. Okay, good. Recording started. So as I said, we're looking at system in state variable form described in this way. Apologies that I forgot to put on the recording earlier. So, okay, it's written in this particular structure because, as I said, many practical systems fall into this structure. All right, so with this, then, again, in the first part, we are not going to talk about adaptive control first. We say, okay, you give me a system in this structure. How will I do control? Right, so if you have taken 5101, or my several students down here taken 4302 with me last semester. Okay, you give me a system like this, all right, I'm not talking about adaptive control. How will I do just control, full state feedback control, because all the state variables are measurable? All right, so again, I say this is the kind of performance I want specified through a reference model. Okay, we'll look carefully at what this particular thing will mean in a moment. All right, so it's specified in this particular way through a reference model. Okay, so given this system, how will I do my control? Okay, clearly. So as I said, even in 5101, all right, also in my 4302 module last semester, we have looked at that. Okay, this system, the full set of state variables are available. So obviously, the simplest way is to do full state feedback. All right, simplest way is to do full state feedback. And so full state feedback will now be, all right, you take your feedback gain. So here I'll just label it as, because we're doing adaptive control, so this terminology, this way of writing is quite normal. I'll put my state feedback gains as the vector theta x transpose my state variables, because all my state variables are measurable. And then the easiest way is to put in the scaling gain. So I'm sure in your 5101 you have seen it, because certainly in my 4302, my students work with me, we've done this. Okay, so you do this full state feedback with the scaling gain. And of course, just like, that's why we carefully develop the first order methodology, because we are going to use an approach which pretty much parallels the simpler first order. Okay, so now what's happening down here is that, okay, this is my control, right? Theta x transpose xp plus theta, the scaling gain r times r. All right, and then okay, I can always rearrange it. If I rearrange it, right, this will now look like AP, all right, plus GB theta x transpose, all right, and this now will be G times theta R, all right, and then I ask you to look at this carefully, all right, I ask you to look at this carefully, basically in this structure now, all right, in this structure now, all right, in this structure, look for us. Okay, so in this part, we're not doing adaptive control. We're just saying assume it's just like your 5101, like my 4302, whereby in your state variable system, you know all these numbers. You know all these numbers because you're doing linear state feedback control. You know all these numbers, so you know how to set up the system. You know all these numbers down here, and this is the set of state feedback gains you put. Now, find for me, because you know all these numbers, find for me a set of perfect state feedback gains, all right? A set of perfect state feedback gains so that, with this set of perfect state feedback gains, all right, I'm going to get, when I put the perfect state feedback gains at theta x equals to theta x star, that this exactly gives me the reference model matrix that I want. All right. And of course, you would specify your reference model properly as a stable matrix with the kind of sufficiently fast eigenvalues that you want. Okay, so first, this is the first step. You put it down there and you say, look, let it be such that, you will find, assuming you know exactly what it is, you can find the theta star. And of course, similarly, you want to find theta S star such that this now is exactly equals to the GM, so that it now matches exactly what you want to be able to give you your exact reference model, right? And this will be possible because you look at your 5101 or you look at 4302. Basically, these perfect gains exist if you knew the system exactly, and then this is exactly what you would want the system to be a specified performance. Right, so this is what you would do. I mean, this is what you did in 5101 or 4302. Nothing more than state feedback control with scaling gain. All right, okay, then just as in the first order case, which we did so carefully, we said, okay, but unfortunately, even though we want to do this, and we can do this in 5101, we can do this in 4302, but here we cannot because we don't know the numbers in the system you want to control. So, okay, just as before, we don't know the numbers, never mind, we don't know the numbers, never mind, right? We don't know the numbers, but we already know that that particular way to do the control law works. All right, the state feedback. All right, with the state feedback gains, multiply all the measurable state variables. The scaling gain, all right, multiply my reference input. Okay, except because I don't know the numbers, now what I need to do now is all my state feedback gain, all my scaling gains, I now have to make it time varying. All right, and I make it time varying. If I make it time varying, I have to tell you, all right, we have to design the time variation. All right, so we have to design the time variation. So how will we design the time variation? So actually it builds up from the development in the first order system, which is why we spend so much time carefully doing the first order system, right? So, okay, it turns out that the way it builds up for the first order system would be that, okay, again, I need the equivalent of the sign of KP. So now it will be the sign of G. Remember I said I'm able to pull up that number. G is a scalar number, all right? So it's a scalar number. It's not known, but again, in this method, I use the sign of G. So for example, in your CA3, and last time when we're actually doing it on the motor, all you need to do is just to run a simple step on the motor, see which direction its velocity go, right? If you put in a positive voltage and basically it spins in a positive direction, then your sign of G is positive. If you put in a positive voltage and it spins in a negative direction, then your sign of G is negative. So it's very easy. Okay, so it's very real too, because you can actually do it on real systems. All right, so sign of G. All right, then instead of the small scalar number, because now we are working with a whole set of state variables now, it's not just YP. Okay, so instead of just the scalar gain gamma 1, this now generalizes to the capital gamma matrix. And gamma 1, remember, was required to be positive. So here, what is required of the gamma matrix is that it should be symmetric positive definite. All right, so go and check out your undergraduate mathematics, what a symmetric positive definite matrix is. All right, so it should be capital gamma. All right, if let's say, you don't really know how to choose your capital gamma, you can still choose gamma 1 as in the first order case, all right, and make it gamma 1 times the identity matrix. If you take gamma 1 times the identity matrix, it will be positive definite as long as your gamma 1 is positive, and identity matrix is symmetric positive definite, so that will also be okay. All right, but the full symmetric positive definite matrix is helpful because it gives you more flexibility rather than just gamma 1 times identity. But that will also work, okay? Then what then happens is that, remember we had the tracking error. So now there will be an equivalent tracking error. The tracking error will be in all the state variables. I'll talk about that more in a moment. So this is a whole vector of tracking variables. Then it will be transpose P, a symmetric positive definite matrix, which I'll tell you later on in a moment. Then times the B input vector of the system. Remember we said B was known, and that's realistic for a large class of real systems. And then finally, remember your full state variable, which is measurable, right? Your full state variable, which was measurable. Okay, right, so that is down there. Okay, so that's down there, and then similarly, okay, that the scalar gain is just a single scalar gain, so that's more like a simpler version. So again, you need minus sign of K, sign of G. All right, because it's a simple gain, you can just put a simple positive number gamma. Okay, the same tracking error combination will come in E transpose PV. All right, and now of course this is for the scaling gain for the reference signal, so times R of T, and that will be your adaptive law. Okay, but I need to say more. All right, I need to say more, and first of all, the tracking the whole vector of tracking errors that's generated from, all right, the whole vector of tracking errors that's generated from E equals to your measurable set of state variables minus XM. XM is from the reference model that you generate. So you generate the reference model, so you know all the state variables in XM. All right, so gamma is any, as I said, n by n positive definite matrix, symmetric positive definite matrix. Gamma is any scalar greater than 0. All right, and that P comes about, remember, as we said earlier on, following from the development of the Lyapunov theory, that this P, all right, will come from, this P will come from. So remember, you have now, for your system, right, already set up your reference model. Your reference model will be stable. So AM is a system matrix from your reference model. AM will be a stable matrix because your reference model, you will set it up to be stable sufficiently fast up to what you want. So AM is set up by you is stable. So this now comes from that equation from the earlier Lyapunov-based theory that we said before. AM transpose P plus PAM equals to minus Q. All right. Okay, look at this carefully. AM is specified by you because you will specify the reference model. Okay, AM is specified by you. You will specify the reference model. So AM is known because it is given by you. Then here in this design of the adaptive controller, you will also specify a Q matrix. And the only requirement for the Q matrix is that it is any symmetric positive definite matrix. Any symmetric positive definite matrix, but you have to specify it. So for example, one example would be identity. Identity is a symmetric positive definite matrix. You put identity, all right? And then you solve for this equation because AM is given by you. AM is given by you. Let's say you put identity, you solve for this. It's guaranteed that a P will exist. You saw before, guaranteed that a P will exist. And the P itself will be symmetric positive definite. So AM is designed by you, given by you. Q you specify, all right? And then you calculate and put your P, and then you put your P back into how you will do your adaptation. So everything now needed for adaptation is in here. Okay, now Q is any symmetric positive definite matrix. So at this stage, it can be anything. All right, similarly as in previously, even in the first order case, we said the gamma can be anything. But of course, even though they can be anything, later on in your CAs, you will get a chance to experiment with it. Okay, different choices of gamma, capital gamma, the matrix, small gamma, the positive gain, different choices of Q, all right? would affect the performance of your adaptive controller. Okay, you will have to analyze it. This is what I expect out of you from your CA. Go and look at it, understand it on what's happening with your different choices. Okay, so here, but here, basically in the theory, you just specify anything. So Q can be identity. Q can be some number, all right, some number, some Greek number. I was going to say Omicron. Omicron is a very bad word. I mean, it's the name of the virus. But Delta is also the name of the virus. I never mind. Some Delta times identity, and your delta can be small, your delta can be huge. As long as delta is a positive number, it also obeys this. And it will all work. The theory will all work, but the performance will be totally different. Okay, the performance will be totally different. So you will explore that in your CA1, in your CA3, right, for this. Okay, so this would always be possible. So now that we have been able to completely set up all of these things, let's now make sure that this really works. All right, even though we say it scales up from the first order. So how does this work? Okay, so as usual, what we do is we said, okay, go back to all these things. All right, so now what then happened is, okay, fine. What then happens here is I go back, take what I put for the control, because x dot equals to APXP plus GBU, and U was theta x of t transpose XP of t, right? Then plus theta R of t, right? Times R of t itself, right? We said that, but we also know that, hey, just as before, all right, this perfect number exists for this, all right? And it's basically, this thing would actually be basically the perfect number plus whatever error is there. Okay, same. So this thing would be whatever perfect number plus whatever error is there. All right, then with that, then as before, we collect the whole thing together, all right, and then rearrange. And then if I now rearrange that in that equivalent way, this would now be AP. Okay, I separate out the part with the perfect numbers. This will be GB theta X. One moment. Okay, so let me put, okay, theta X, right? Star, the exact ones transpose. And this one, again, you put the exact one, G theta R star. And then, of course, we can separate out the error parts, all right, which would be P X transpose of T, XP of T, plus P R of T times R of T, right? So we've separated that out. Then similarly, we can now begin to collect these things together. All right. So clearly, as we said, the set of tracking errors that we have is the set of state tracking errors, right? XP, which you can measure. XM is what you generate. Okay. So this is the state tracking error. So you can go ahead, all right, similarly as before, it may be a bit more messy, but you now, all right, E is XP minus XM, so E dot will be XP dot minus XM dot, all right, and if you now go and expand this out, you should be able to write this out as AME plus PX transpose XP plus PR, all right, times R. Okay, you should be able to get that. So with that, we now have the required expression, all right, of interest for E dot. Okay, so we have that. Okay, then in addition, all right, this one is not this next part is not too different from the earlier simpler first order case in lecture 1, because this one basically we are also interested in phi x dot and phi r dot, but you would be able to very straightforwardly and clearly see that, look, basically phi x is just nothing more than your adaptation law then of theta x dot, because that's exactly what you generate, because phi is theta x minus theta x star is a constant. So basically theta x dot is exactly phi dot, which is what we had designed, which was minus sine of g gamma E transpose PB times x of p. So we have that. So similarly, this is nothing more than the adaptive law for theta r, all right, which would now be minus signum g, all right, gamma E transpose PB times r. Okay, so we've got that. Okay, we've got that. And with that, then what we can do is we can proceed in a similar way. Basically, we are looking for the scalar function, all right, that the Lyapunov function candidate, ellipsoid, whatever you want to call it. All right, so now what I can do is I have E, which is one whole vector of dimension n, this of dimension n, right? This of dimension n, which is the error in the between my state variables and the reference model state variable. All right, so this is n dimension error vector. Then I've got these basically these adapted parameters. Right, so I can collect together. Okay, so phi x is, remember, the n state feedback gain, the parameter error in the feedback gain of the n state feedback gain, the perfect state feedback gain, right? So this is the state error in the perfect state feedback gain. This is the error in the scaling gain. I can collect them together. This, of course, will be of dimension n plus 1. All right, but it doesn't matter. Okay, it doesn't matter. I can just collect them. All right, so if I now collect them, okay, together, I can write it in a very compact, convenient form. And I say, okay, my scalar function that would be of interest will be 1/2 of E transpose E. All right, I need to find the proper shape. The proper shape turns out to be P. Okay. Then the other one will be 1/2. All right, it will turn out to be magnitude of G in the same way as previously, magnitude of KP. And then it would be phi, all right, that this n plus 1 error vector, all right, phi transpose phi. Okay, then what will happen is that I will need remember, it was 1 over gamma 1, 1 over gamma 2. Now it will turn out to be basically the inverse of the larger gamma matrix, where in the gamma matrix, what I've done is I've basically taken my earlier gamma, but also put in the small gamma for the adaptation of theta r. Collect that together. This will be n plus 1 by n plus 1. I put it in here. I take this inverse. So that would be how I will need to kind of put in those numbers to shape it. Okay, then now, of course, this is my scalar function, my Lyapunov function candidate. Then what I'll do is I will go and take the derivative. It's not difficult. Okay, this is just basically now same kind of a thing, except in vector matrix form. So if you take the time derivative, it will turn out to be very straightforward. All right, not difficult. It will just turn out to be in a quite standard, okay, because that one is 1/2 of E transpose PE. So it will just basically differentiate out to be 1/2 All right, E will be there. E trans, okay, no, because it is E transpose E, so it's like a square. So there will be two parts to it. So it will be 1/2 of 2 E transpose P, and then you have to differentiate E, which will be E dot. Okay, that's the first part. All right, then similarly, that second part is also there, 1/2. All right, and that one will be 2 times also magnitude of G, and it will be P transpose gamma bar inverse, and then you will get that P dot uh, in there after differentiating with respect to time. All right. Okay. Now, what I'll do is I'll carefully write this thing out. All right. I'll carefully write this thing out. Remember how P was generated from the earlier calculation. Okay, so P was calculated from the earlier calculation, and also remember where E dot was, because we have already generated the equation for E dot, right? So E dot is down here. So now let's put all those things in. All right, let's put all those things in. So this now will be basically, now I put all those things in, and it will be S in the top, right? S in the top, AM times E, all right, plus G B P transpose. Let me now capture all the relevant signals together and write it as X bar in a more convenient fashion. All right, because remember, I've also made this to be n+1 dimension. All right, the errors in theta and the errors in theta r. So if I now rewrite this as n+1 dimension by putting the xp and the r, right? So now this will match because it's n+1 and this n+1. Okay, so this part I've expanded because this is E dot, right? This E dot, so I expanded. This other part, okay, let me leave it alone first. This other part, let me leave it alone first, so I let it remain down here. Okay, now that I've done this, let me then next carefully look at this first part. Carefully look at this first part. I will still come to this part, but let me carefully just look at this first part. All right, and the way I will look at this first part is, okay, first of all, I will use a result which you would have seen somewhere in your linear algebra, your when you do matrices and all that. It's a very simple result, but a very clever result. Okay, this very simple and clever result, all right, just says this. You give me any matrix. You give me any matrix at all, okay? Any n by n matrix. You give me any n by n matrix. I will always be, so this result says, you give me any n by n matrix, I will always be able to write it out in this way. 1/2 of m plus 1/2 of m. All right. I mean, it will work because m will be always 1/2 of m plus 1/2 of m. Okay, then it says, let's do more than that. Take that m, transpose it. All right. And if you take the m, transpose it on this side, you must minus that m transpose on the other side. And then the expression is still correct because all that happens is that m is indeed 1/2 of m times 1/2 of m. Then this m transpose that you take here, which you minus away, just cancels each other out. And it says that I can write m in this way, except that this way of writing it out, which is a decomposition, it decomposes any n by n matrix into a part which is always symmetric. You go and check, this is always symmetric because you take the transpose of this part, it is always itself. So that's why it's symmetric. Then this second part is always anti-symmetric, which means that when you take the transpose of itself, it will always be the negative of itself. Okay, so this is basically a very nice decomposition, which takes any n by n matrix, all right, and then decomposes it into a symmetric part and an anti-symmetric part. But more important than that, okay, you go and double check for a symmetric matrix. For any matrix where you have its symmetric decomposition as anti-symmetric decomposition. All right, if you now take its quadratic form, which means that now n by n matrix, all right, if you take any n vector, all right, and form a quadratic form, which means that, okay, let's say a quadratic vector q of dimension n, q transpose m times q. All right, and you take the quadratic form, you will find that this decomposition shows you that when you take the quadratic form, this part of the quadratic form always turns out to be 0 because q transpose mq minus q m transpose q. Okay, because m transpose, quadratic form is a scalar. When you take the transpose, the whole thing cancels out. So it turns out that this decomposition is valuable in the sense that when you take a quadratic form, only this part remains, which is what we will use. Because, all right, as I said, you take any quadratic form, all right, it will turn out to be that, all right, the only thing that remains will be from the symmetric part. All right, it will just be from the symmetric part, which is a property we will use. Okay, so now we will use it because now we will go back to our system. All right, we go back to our system and remember what we had. We had this, and now what we will do is, all right, this is a quadratic form. Okay, this is a quadratic form. All right, this is a quadratic form. This is the M matrix we are interested in. All right, this is the M matrix we are interested in. So now we will take this matrix, all right, this quadratic form, and rewrite it out. It will be now E transpose. All right, now that M matrix in there, all right, it will now, we just take its symmetric part. Its symmetric part will be M, which is PAM. All right, and then its anti-symmetric part, which would be PAM transpose, all right, times E, and that will be the quadratic form because the contribution from the anti-symmetric part does not come up at all. Okay, now carefully look at all these things. All right, because, okay, this PM is here. Okay, now take its transpose and then expand it out. Remember, P itself, by the Lyapunov property, was guaranteed to be a symmetric matrix. AM is not necessarily symmetric. So when you expand this out, this will be now AM transpose P transpose, but P transpose is P itself because P is symmetric. Okay, so now this will now turn out to be, all right, 1/2. I pull out the 1/2. All right, E transpose, okay, P AM. Okay, that's the first part of that single matrix. Then this now will be AM transpose, and then PP transpose, but P being symmetric, P transpose is itself. All right, then E. But now look at this. Look at this, how it's turned out, because now what happens is that, all right, in this expression down here, this was how you have used it in the design, because in the way that you design it, this was equals to minus Q. This was equals to minus Q, and Q was selected by you to be symmetric positive definite. All right, so with that then, okay, you can go and check. All right, if you now begin to expand all those things further, this will now expand this out to be minus 1/2 of E transpose QE. All right, plus, okay, the remaining parts are all still there. I still get the E transpose P. Okay, you can check from the above. They are all still there from the above. E transpose P, G, B, P transpose X bar, which is the expanded X vector, all right, n plus 1, which is basically this XP and R. All right, then go and take a look at the other part. Okay, the other part, all right, the other part, which would just be completely, okay, give me one moment. All right, the other part, which would just be completely down there. This would be from earlier. I'm just copying it down. Magnitude of G, all right, P, which is the n plus 1 error vector, which we had written. All right, gamma bar inverse, n plus 1 by n plus 1 gain matrix. All right, then phi dot. Okay, go and carefully check your phi dot. Go and check your phi dot. Okay, basically remember that your phi dot, all right, the way that it turned out would be exactly this. All right, exactly this, and then go and carefully check this out. Minus sign of G and number the G will give you the number G itself, which is here. Okay, so the whole thing down here, all right, once you put this down here, the whole thing now has that part. All right, no, sorry. Okay, I am too enthusiastic. The P dot didn't have this. All right, sorry. But remember, I had minus signum G. So minus signum G times this thing down here. All right, will give you the G. Okay, then P dot was gamma bar, gamma inverse bar, and gamma bar disappears. Okay, then I get P transpose E transpose PB. All right. Okay, E transpose PB is a scalar. You can double check. All right, this is n by n. This is n by 1. This is 1 by n. This is a scalar. So a scalar, I can put it anywhere I want. All right, anywhere I want is a scalar. All right, so then P transpose is a scalar. So this is P transpose X. All right, similarly here, G is a scalar. E is n by 1, n by n. B is 1 by n by n by 1. So E transpose PB is a scalar, G is a scalar. I can pull it out anywhere I want. P transpose X bar. I pull this thing out anywhere I want. This knocks each other out. I just have P transpose X. And you can go and double check carefully that in this design, all right, it's a typical way to now design these things. All right, that you will see that this one basically allows me to completely now cancel that out. All right, it allows me to cancel that out as a result of my adaptive control design. All right, leaving me now with, okay, V dot equals to, okay, V dot equals to minus of 1/2 of E transpose QE. Remember, Q was chosen by you. Okay, symmetric, positive, definite. All right, so with that, then pretty much the rest of it, even though now it becomes a vector of signals, but the development essentially follows along the same line because of the same kind of observations as well. This assures us now that the entire set of signals, error signals in E, all right, the entire set of parameter errors in my X, all right, because remember my scalar function, right? My scalar function V has E, all right, and also has all the parameter errors. So I've shown that this scalar function never ever grows. So by the same kind of result, now I have the equivalent that what now happens is that norm of the E parameter, the vector of errors in the tracking error phi of R. This is just a scalar, but never mind, let me uniformly write it as the norm. That these are now bounded for all time. Anytime that you start. All right, and you can start anywhere. All right, then similarly, you can go and take this, integrate this in the same way, so that square integrable property also holds. All right, then of course this belongs to the class of L2 signals, but again the danger still exists down there of spikes. So again we check the E dot, you can check and see it's bounded. So together then this again gives us exactly what we want in this adaptive control design, that with the two things above, indeed we actually get exactly what we want, that indeed limit as t tends to infinity of norm of E of t from the above. All right, which is basically the tracking error in your state variables compared with the reference model that you want. This is how you want it to behave, because the reference signal is how you want it to behave, right? So this is now coming out to be such that limit of this actually now is exactly equals to 0, which is the design your adaptive controller. All right, basically as a theoretical result, it has to be written as a limiting result. All right, limiting result. But you will see, all right, you will get a chance to see this in your CA3. This is essentially much of the thing for your CA3. If you now begin to later on work on your CA3, even though this is a limiting result that t tends to infinity, you will find that this design is actually very, very efficient. Not only, of course, now your CA3 is all simulation, but even in the earlier days before pandemic, when we actually use the motor, you will see actually, even though it's a theoretical limiting result, what actually happens is the adaptive controller adapts very, very quickly. All right, very, very quickly, typically within 3 cycles of a periodic tracking error signal. So this works very well. Okay, with that, then, okay, I would say I'm very happy to stop. I'm not, my students know I don't, in each class, I don't want to push too many results. I just want to push 1 or 2 key results, but the 1 or 2 key results, I want you to learn it, and I want to let you to learn it well. Okay, with that, I'm done. Okay, I'll stop the recording.